my name is Seonhong Min, and as Ben introduced, I am a first-year PhD student in Seoul National University, and I will be presenting faster TFHE Bootstrapping with block binary keys today. This is a joint work with Changmin Lee and Jin Young-seo and Yong-soo Song. So let's get into the notion of fully homomorphic encryption first. So FHE is a crypto system which supports arbitrary function evaluation on encrypted data, and it can be applied to a variety of applications such as privacy preserving machine learning, PPML, or PIR, or PSI. So the most of the efficient FHEs to date are built over the learning with errors problem and its variant ring LWE. So in a nutshell, LWE problem is that if you sample A from a uniform distribution and given secret key and some small error, then if you set B equals minus inner product of AS and plus E, then AB is computationally indistinguishable from uniform distribution. And RLWE is a ring variant of LWE, which is defined of a cyclotomic ring, but usually we use power over 2 cyclotomic rings. So the most of the FH schemes are based on LWE and RLWE problems. So there are BZV, BFV, CKKS, which support SIMD operations over encrypted data, and we have TFHE and FEW scheme, which usually do not support the SIMD arithmetic. So today we will be focusing on TFHE scheme. So TFHE is a FHE scheme which supports bit operations. It can be extended to integer arithmetic, such as it is already implemented in TFHRS, but we will be focusing on the bit operation to make it more simpler. So for the secret key, it consists of 3 different secret keys. Firstly, S, which is LWE secret, and T, a ring polynomial with binary coefficients, and a vectorized secret T, which is a coefficient vector of the ring polynomial T. So all keys are sampled from binary distribution. And also for encoding, if you have a bit -1 or 1, then you can encode it as follows: Q over 8M. And to decode that encoding, you just want to see if it is bigger than 0 or not. So for the encryption, you firstly sample A from a uniform distribution and E from some kind of small noise distribution, and then you set B equals minus inner product of AS plus mu plus E, where mu is an encoding of a single bit. Then the encryption of the encoding is given as C equals B comma A. And to decrypt that ciphertext, you just simply compute B plus A comma S, inner product of A and S. So how to evaluate a homomorphic gate homomorphically with TFHE scheme. So for 2 input ciphertext C1 and C2, you firstly compute a linear combination of 2 ciphertexts with respect to the Boolean gate. So for example, NAND can be evaluated as follows: C equals Q over 8 minus C1 minus C2. So after the linear combination, since it computes the sum or linear combination of 2 ciphertexts, it may contain a large noise. So we need a costly operation called bootstrapping to reduce the size of the noise for further evaluations. So for example, before the bootstrapping and after the linear combination, the error can be have the bound of Q over 8, but after the bootstrapping, it can be reduced to Q over 16th. So the TFHE bootstrapping, it consists of 3 different steps. Firstly, blind rotation, sample extract, and key switching. So in the blind rotation, in a nutshell, you homomorphically compute the decryption circuit over the exponent of x. So in other words, x to the b plus inner product of as. So to realize this, you need blind rotation keys, which is RGSW encryptions of SI. And for sample extract, it's just extracting the constant term of the plain text from the resulting RLW ciphertext. And finally, key switching. It switches the dimension of the LW ciphertext. So to realize this, you need key switching keys, which is gadget encryptions of TI, which is also known as LEV encryptions. So as you can see, blind rotation requires the elapsed time of blind rotation is about 9.4 milliseconds, and the key switching is 1.1 milliseconds. So blind rotation is very heavy. So what we wanted to do was to make the blind rotation more faster. So the motivation is that most of the FH schemes such as BZV or FV or CKKS, they make an additional assumption on key structure to obtain better efficiency. So for example, in BZV and FV, if the key is sparse, then the noise growth is smaller in homomorphic multiplications. And also for BZV and CKKS, if the key is sparse, then the bootstrapping depth is small. So what we did is to adopt that kind of similar approach to use a sparse secret to accelerate TFHE scheme. So firstly, we made the blind rotation more faster by sampling LW key from a distribution called block binary key distribution. So by sampling LW key from that distribution, we can reduce the number of the FFT operations. And also, we can make the key switching more compact by reusing the LW key as a part of our LW key. So by that, we can improve both time and space complexity. So let's begin with the blind rotation. So as I explained earlier, its functionality is to evaluate the decryption circuit over exponent of the monomial. So in reality, you have a ring polynomial with pre-assigned coefficients called the test vector. So if you compute test vector times x to the b plus as, which is TFHE times x to the q over 8 m plus e when m is the message, then the constant term of TFHE times x to the q over 8 m plus e equals 8 over qm with pre-assigned coefficients. So to realize this goal, we homomorphically multiply monomials x to the aisi to TFHE times xb iteratively. So we need n homomorphic multiplications, which is external product, and which is multiplication between RLW ciphertext and RGSW ciphertext. So the observation in TFHE blind rotation was that x to the aisi can be written as a linear sum of si, say 1 plus x to the ai minus 1 si, so that if si is binary, say we make the encryption of x to the aisi, and then we multiply it to the test vector iteratively. So we need to generate x to the aisi, the monomial, and then you have to multiply it to the accumulator for n times. So since the external product is very heavy and costly operation, we want to reduce the number of the external product. So let us check if we can multiply two monomials simultaneously. So if you just write it down, then you just you can easily see that x to the a1 s1 plus a to s2 can be written as a linear sum of s1 s2 and s1 s2. So with this formula, you can actually reduce the number of homomorphic multiplications by half. And also, it also brings some kind of, so it's actually faster, but it requires an additional RGSW encryption of S1, S2, and S3, S4. And also the number of the linear evaluations grows, as you can see in the equation, the blue part. So we thought, what if you can ignore the case where S1 and S2 equals 1? Then S1, S2 is always 0. So you don't really need the additional blind rotation key of S1, S2. And also the number of the linear evaluation remains the same, whereas the previous approach requires exponential growth of the linear evaluation. So we generalize this observation to L monomials at once, and it is possible. And if the secret key was sampled from a distribution called block binary key distribution. So in a nutshell, the block binary key distribution is a distribution where n is given by KL, and the secret key S is it is some kind of concatenation of k different blocks, and in each block there is at most one in each block. So it will be much easier if you look at the figure. So as you can see, there is only one or no ones at all in each block. So if the key was sampled from block binary keys, then you can generate the x to the sum of AISI more easily just by computing the linear sum of the RGSW encryptions of SI. So in the previous approach in TFHE, we can multiply one monomial with just one multiplication, one addition, the constant multiplication and addition. But if the secret key was sampled from the block binary key distribution, then it can be written as a linear sum of SIs. Say we can multiply L monomials with one multiplication and L addition. Say this is our blind rotation. We generate L monomials at once, and then we perform homomorphic multiplications, a single homomorphic multiplication to multiply that monomial, L monomials, to the accumulator. So with this approach, we only need k external products are required, but we have to remark that it does not lead us to direct L times speedup, because it also requires other operations such as FFT or floating point operations and addition or multiplications. So this is the exact algorithm of our blind rotation. So as you can see from the line 5, you have the accumulator, which is initialized with x to the b multiplied by the test vector. And from line 6 to 8, you iteratively generate the monomial, the RGSW encryption of L monomials at once, and you multiply it to the accumulator with a single external product. But the problem is that you have to generate the RGSW encryption of monomial, and it is very heavy because it requires more floating point operations, because RGSW encryptions are huge. So instead, we can just reuse the gadget decomposition of accumulator for each external product. So for example, we don't need to generate the encryption of monomial, but instead we just compute the external product of HCC, the accumulator, and its blind rotation keys, but reusing the decompositions of HCC. Say this previous method and modified method are essentially the same, the functionality is the same, but the number of the FFT operations is reduced with the same number of the floating point operations. So in the previously, the floating point operations were, there were more floating point operations than the original TFHE scheme, but with this modified hoisting technique, we can just reduce the floating point operations. We can reduce the number of the FFT operations with the same number of floating point operations. So this would be the very crucial part of the block binary keys. So we have to talk about the security of block binary keys. So is it really secure to use the block binary keys with such structure? The answer is yes. So asymptotically, if the entropy of the key distribution is sufficiently large, then the LW problem is secure with such key. So the entropy of the block binary keys is L plus 1 to the K. So if we set L and K big enough, then we can keep our LW problem with block binary keys secure. So, but this is not enough. So we also conducted some cryptanalysis considering the best known lattice attacks, such as dual attack and meet in the middle attack. So we also devised some kind of tailor-made attack which can effectively attack the block binary keys using its structure, but they were not very effective than dual attack and meet in the middle attack. So we won't be covering tailor-made attack in this presentation. So if you're interested, you can just look at our paper. So for dual attack, so dual attacks on LW is very effective when we are using sparse secrets. So just ordinary dual attack does not it does not assume the block binary secrets. So we can just simply run the lattice estimator with respect to the expected Hamming weight and over L plus 1 and LW dimension n. But still, since one can reduce many dimensions by guessing for the block binary keys. So for example, if you get it right just for one block, then you can reduce L dimension just one block at once. So we can think of some kind of modified dual attack. So one can reduce T blocks by guessing, and then you can exploit dual attack to the remaining LW problem. So then the cost is L plus 1 to the K, L plus 1 to the T times T, where T is the cost of dual attack on LW of dimension n minus TL, the remaining blocks, and the secret with expected Hamming weight n minus TL over L plus 1. And also we can think of the meet in the middle attack. So meet in the middle attack is, in a nutshell, when given secret S, you can split the secret vector into S0 and S1. So, and the Hamming weight of S0 and S1 is approximately half of the Hamming weight of S. So when you're given an LW instance BA, then B plus S0A is approximately minus S1A because B plus A is small. Then we can find the collision between two sets, R0 and R1. So basically R0 is all the possible values of B plus X0A, where X0 is possible secrets, and R1 is all the possible values of minus X1A, where X1 is possible S1s. So since the cardinality of R0 and R1 is approximately square root of S, the time complexity of meet in the middle algorithm is approximately square root of S. It was the meet-in-the-middle attack was recently improved by May et al. In 2021. So it is, in a nutshell, inductively perform meet-in-the-middle attack to S0 and S1 as well. So overall cost requires S to the 0.28 time complexity, where S denotes the entropy of the secret. So we can just think of the worst time complexity, so the worst case. So since the entropy of our block binary key is L plus 1 to the k, the cost of this meet-in-the-middle attack will be 2 to the 0.28 k log L plus 1. So it means that it achieves 0.28 k log L plus 1 bit security. Let's get into the details of the compact key switching then. So the functionality of the key switching is to switch the secret key of LW ciphertext from T to S. So given LW ciphertext C encrypted under T, then you can compute C prime as follows. The trivial encryption of B plus sum of I equals 1 to n AI gadget decomposition and encryption of TI. Say if you decrypt C prime, then you obtain approximately B plus sum of AITI, which is decryption of C. So this key switching it satisfies the functionality of key switching, but the time complexity and space complexity is since it requires n homomorphic scalar multiplications and key switching keys, the time complexity is O. Also, space complexity is O(n) as well. But we can make it more compact by reusing the LW randomness to the RLW secret randomness. So if we set TI equals SI, then we can replace C prime by BA1 AN plus sum of AI encryption of TI, where I runs from n plus 1 to n. Then the decryption of C prime equals to B plus sum of AISI, where I runs from 1 to small n, plus sum of AITIs, where I runs from n plus small n plus 1 to large n. Then it is equals to decryption of C under secret T. So it still satisfies the functionality of key switching, but the time complexity is drastically reduced, since its time complexity is n minus n, since it requires n minus n scalar multiplications, and the space complexity is also reduced to n minus n. If you look at this figure, then it will be more easier to understand. Say in the previous work, you had to change all the green cells to blue cells, so the time complexity was larger. But in our work, by reusing the LW secret as a part of our LW secret, you don't need to change those blue cells. So you only need to change large n minus small n green cells to blue cells. So the time complexity will be reduced to from large n to large n minus n. So about the security of this compact key switching, reusing the LW as a part of our LW, we couldn't really find an effective attack on this secret reuse. So we can just simply assume that it's secure. So we can think of its security as with respect to the dual attack and meet-in-the-middle attack. So we can estimate its security by running the lattice estimator with LW dimension large N and with the expected Hamming weight N over L plus 1 plus large N minus N over T. And for the meet-in-the-middle attack, since it does not really depend on the distribution of error, so the security relies on the LW security, so we don't really need to care about the meet-in-the-middle attack. So let's get into the parameter selection. So as I explained earlier, we set the parameters with respect to the dual and meet-in-the-middle attack. So if you look at table, usually meet-in-the-middle attack is more effective than dual attack. So you can just set the block key parameters with respect to the meet-in-the-middle attack. And since meet-in-the-middle attack, it depends on the entropy of the secret. So we have some kind of equation to compute given L, compute K given L. So if you want to make your own block parameters, then you just you can just set K as follows and given L. Also, but you also need to run the lattice estimator if it is possible against the dual attack. So let's get into the implementation details. So as you can see, it is implemented based on the TFHE library, and it achieves 1.5 to 1.6 speed up compared to the original TFHE library. Also, the key size is reduced by 1.8 times. So one thing I want to remind is that since we reuse the randomness of the LW secret as a part of the LW secret, the key size is reduced to large n minus small n. So it seems that the time remains the same even if we increase L. The key size is reduced a lot. So it also you also have to think of the key size when you are choosing the parameter for the block binary distribution. So it can be applied to lots of things. So it also can be applied to many kinds of TFHE like crypto systems, since it works as long as the algebraic structure, the block binary key structure remains the same. So for example, programmable bootstrapping or without padding programmable bootstrapping or Chimera, they just make use of TFHE bootstrapping, so it works very well. And also for the multi-key TFHE, since the secret key of the multi-key ciphertext is the concatenated vector of its secret key, the block binary key structure remains the same. So it also can be applied to multi-key TFHE. And also it can be applied to AP few style crypto systems. We just think of block n array distribution. It means that there can be only one non-zero component in each block. So originally keys were given by RGSW encryptions of x to the JBK SI, where J runs from 0 to B minus 1, and B is the some kind of base for decomposition. And it in LMKC plus 22, the keys were given by RGSW encryptions of x to the SI, but it really doesn't matter when it comes to the block binary key distribution. So instead, you can provide RGSW encryptions of 0 if SI is 0, then if you just write it down, then it is very obvious to how to apply block binary key distribution to these kind of schemes. But when it comes to multi-part TFHE, and out of n threshold TFHE, then since the secret key for MP ciphertexts is the sum of its secret key, which is called the joint key, so it breaks, kind of ruins the structure of the block binary key distribution. So it can be applied to kind of naive solution, but it can't be applied to the state-of-the-art scheme such as LMKC plus 22 or PR23. So for the multi-key TFHE, I have implemented to the multi-key implementation. So as you can see, we achieved 1.7 to 1.9 times of speed up. So the performance improvement is actually better than the single key scheme. I think it is because the multi-key RGSW external product is a bit more heavier than single key case. And also the size of the key switching key is also reduced as well. So I think it would be great to apply block binary key distribution, this kind of TFHE acceleration technique to multi-key TFHE or multi-party TFHE or other schemes. So for the implementation, if you are interested, the source code is available at our GitHub. So there are the first one is the original implementation for the TFHE scheme, and for the second, it is a multi-key implementation which is written in Julia, and for the third, it has PBS implementation. It is written in Go, and it was developed by our colleague. So if you are interested, you can just visit any of these links and check the code. So thanks for listening. So if you have any questions, I will be happy to answer. Thank you.